Right, good morning. Here we are again. And this time I travel all the way from Bristol to Bristol. So actually with me, the ACCU is rarely causes much of a change in scenery. Although this morning it is absolutely miserable and grey. I'm trying to work out which pencil shade of grey it is in Bristol. It is also wet. So one advantage of being at home is that I can actually stay dry. So what am I going to talk about? What is this talk about? This talk is about an hour and 20 long. And please ask questions in the Q&A. I have the Q&A up on my left-hand side. I have a chat window up on my left-hand side. I won't be monitoring those as I'm giving the talk. I might glance over and notice things. But I will try and get some time at the end to pick up some kind of questions, because the normal ACCU to and fro, the casual style with which things get interrupted, it's difficult on Zoom. So that's something we have to accommodate. So what am I going to talk about? It depends. So what does it depend on? Let's start with this idea that everything begins in silence. And I want to talk a little bit about skills and knowledge. Which immediately might turn you off and not sound very exciting, but bear with me, okay? Begins with nothing, then you start something. You are a novice, okay? It doesn't matter what your experience in something else is, you are a novice, okay? Maybe you're a programmer and you already have many programming languages under your belt. You decide to try a new one. Guess what? You're a novice. Oh, but I'm an experienced programmer. Doesn't matter, you're a novice. That's the first thing to remember. One of the worst things we end up with is the idea of the expert beginner, somebody who assumes they can simply teleport from one altitude to another. Because they're an expert in this, they become an expert in this. So I remember working with a C programmer many years ago, and I was working on C++, and my colleagues were working on C++. The C programmer came over and started criticizing our C code and saying, oh, you don't need those ampersands everywhere. And it's just like, but that's a pass by reference. I don't know what that is, but you probably don't need it. And it's just like, this is C++. Yes, I know, but you know, all those other things and that class keyword, you probably don't need that either. It's like, yeah, he was very strong on opinions. So this is a common phenomenon. It's not unique to programming, but let's acknowledge we are a novice. We should have the beginner's mind. We, with our existing experience, may be able to progress more rapidly through the other stages of learning. And really, it's a case of a progression. Advanced beginner, we become competent, we become proficient, we become expert. Actually, that's not a foregone conclusion. Many people kind of stop here, and that's good enough. Some people progress to there. The pyramid thins out at the top, though. It's not a foregone conclusion you will go all the way. Now, another thing that I want to highlight here, these 5 levels, there's nothing magic about 5. Humans are a continuum. It's just an arbitrary structure. We have to section things off somewhere. This is based on a model, Dreyfus model of skill acquisition. It was formulated by 2 brothers, Dreyfus, back in 1980. One was an applied mathematician and programmer, and the other was a philosopher, and they were really trying to understand expertise and how we acquire skills. Somebody's made the observation, Nicholas made the observation, Dunning-Kruger effect in the chat, and I think it's really interesting that we had to wait another 15 years for the Dunning-Kruger effect to be identified, but it's actually kind of present here when we recognize the notion of the expert beginner. I've seen people use this as a maturity model. In other words, these are the stages you go through. That was not what the Dreyfus brothers were interested in. What they were interested in was the way in which you know things. It's not the progression that you pass through. It's not a checklist. It is the fact that as a novice improves, the nature of their knowledge and how they acquire new knowledge will change, and the nature of how they work with that skill will change. An expert is not simply somebody who does the things that beginners do, just more of them. You know, that's not how they do. If you remember, if you've learned a second or third natural language, you may remember if you were taught it at school, you were taught vocabulary lists and simple sentence structures and grammar and things like that. That's at the beginning. As you become proficient, you don't simply learn bigger vocab lists every day and more grammatical rules. That's not how you acquire it. The nature of your learning changes, your relationship to the subject matter changes. You learn by immersion, you learn by usage. It becomes very different. In other words, we move to a model that is much more intuitive. It's in there. You don't sit there and think, oh my goodness, where does the verb go? And, you know, how do I get this to agree with that and fit these pieces together, these words like Lego bricks? It's just there. It's in the flow. Whereas right at the beginning, everything's analytical. It's broken down. So if you like, this is like a holistic versus decomposed view. More interestingly, what they observed was that there is your reasoning and understanding and your knowledge is situational. Whereas as a novice, it's non-situational. Let me put it another way. As an expert, it is context sensitive. What you are looking at and your judgments are based on a situation, on a context. To truly understand something, you need to look at everything around it. Whereas as a novice, context free, everything is an absolute. So I kind of noticed this yesterday. Yesterday, actually responding to a comment on LinkedIn about something. Somebody was after a word that means something, and they already had a word. And they said, but I need this word to mean these other things. And I pointed out, you want words to do what they're not intended to do, or rather, the word already means that. What you're looking for is a context that makes the word mean that. You're looking at the thing. And I find no matter how many years of experience people have, they often just look at the thing rather than the things around it that actually give it the meaning. In other words, there's a different notion. More importantly, it's the difference here. It depends. That's what happens. That's why people who really know their subject matter often say, it depends. You know, I've got this problem in my code, or should you always do this? It depends, because really it does. Whereas at the novice level, we offer people guidelines and rules. You should always do this and never do that. You can kind of see these in a lot of coding guidelines. Don't do this, avoid this. And those rules are useful for novices, but they are almost entirely useless as you progress. They are like road signs that basically say no entry. You know, you're driving around, you can see where you want to get to, but it's a one-way road and you're not allowed to drive it. What does the sign say? It says, don't do this. You can't come here. It doesn't tell you what to do. It tells you what not to do. That is entirely useless. Now, I remember working with somebody whose programming background was COBOL many years ago. And we were using a programming language that had no jump constructs at all. You know, not even, there's no return that was a jump state, no break, no continue, none of that nonsense. It was a proper programming language rather than these ones we use now. And it was great, except she was sitting there really struggling. She said, I can't work out the control flow for this. And it was one of those things that she said, I know I was always told not to use a goto, but you couldn't help it in the code that we were using. And it was natural in the COBOL dialect. Her thinking was very much bound to that, but now she was left with a problem. Here was a language that said you're not allowed to do it. And she was saying, well, I've tried to solve the problem using gotos, and now I'm taking the gotos out, which is not actually the way to solve it. In other words, it requires a very different thinking model. It requires a different relationship. So Sergey's put undefined behavior there. I'm going to point there is no such thing as undefined behavior, and I will tell you why, and we will get to that. That is actually part of this talk. Now, it turns out when we have this idea of this dependency, this context dependency, this expertise, this is not unique to the Dreyfus model. As I said, 5 is an arbitrary number. You can sit there. I was going to say you can go and sit in the bar and come up with your own n-level model for any given value of n, except you can't really go and sit in the bar, or rather you can if you have a tiki bar at home and you have a very lonely experience. But just imagine, you can come up with your own thing. We see this reinvented many times. There is a concept known as shuhari in Japanese martial arts. I came across this not because I have any knowledge of martial arts, but Alistair Coburn introduced me to this. And it's broken down. It's basically 3 words, shu, ha, ri, and it is to talk about your level of mastery. So here's the kanji, and basically what this stuff means, what each word means, it has very specific meanings. I believe shu means something like obey, and ha means something like detach, whereas ri means leave or separate. I was looking to put something on the slides, but actually I realized I can come up. Let's make this a business talk all of a sudden. I'm now going to give you business advice. I honestly, you know, where's the venture capitalists out there? This is imitate. You must follow what you are told. Do as you are told. Here is the rule. This is the way. Then you start adding variation, innovation. You start exploring the boundaries. As you achieve competence, what happens is those rules, you realize they had exceptions. You start kicking against those exceptions. You start acknowledging those exceptions. You find that the rules are not absolute, that the world is not actually flat, even though from where you sit, it looks flat. You start discovering that there is a little bit more there. And then you discover those aren't exceptions to rules. They are their own rules. They have their own context. And you are free to invent and to leave. And there's this whole idea that what you're actually doing with that is understanding different contexts and discovering and creating new contexts in which ideas apply. So the April columnist, it's interesting to have a columnist who only writes once a year. The April columnist for ACCU's Overload, TDD, in 2008, wrote a piece called The Way of the Consultant. And it was very much about how one should consult and the various levels of mastery. So here we are gonna, what do I think? This code sucks. This is somebody who has not been initiated on the path. They do not yet understand the way. Here is somebody who is at a more kind of infant Padawan level. It's not all bad. Nothing that some aggressive, merciless, and inconsiderate refactoring couldn't solve. Right, here we are at the pre-mastery level. We show early signs of mastery. Although there are some aspects of the system as designed that are sound, the solution as a whole may be better aligned with the needs of the business by leveraging the synergies of complementary solution paths. The resulting amelioration of quality will be further enhanced by displacement of vestigial solution components extant from the status quo. This person is almost there, but not quite. And yet, here is the true Jedi Master. What do I think? It depends. That's how you know somebody's achieved this. So let's kind of take a little journey and look at something that sometimes people hold up as a principle. I want to poke a little bit at some of the absolutes that we normally pick up as novices and forget sometimes to discard. The idea is that as we speak to other people, as we offer advice, we need to understand where they are in the learning process. To tell somebody everything is not useful if they are at the beginner level. Tell them everything you understand, they will look bewildered, and the knowledge will not be useful to them. On the other hand, sometimes we forget to let go of the things that helped us. And it's just like, yeah, that's just a kid's guideline. Stuff like solid. I mean, apart from the fact that solid principles are in fact mostly incorrect, the fact that people insist on those and experts insist on those is, I find, deeply troubling, because at a level of, expertise should mean you say, no, actually, I know what's really going on, and I'll tell you what's really going on. So let's travel to Mars. Last month was Mars month. 3 probes, United Arab Emirates, China, and the US arrived, thanks to a rather convenient positional arrangement that allowed a fast journey time from last July to this February. And one of the things that we can actually, see is that Mars is incredibly dry, super dry. Like, don't repeat yourself. Okay, so this is a guideline. It comes from the Pragmatic Programmer's wonderful book, 1999, second edition, 2019. Often people talk about this just in terms of code duplication. Actually, more broadly, what they're talking about is representation of knowledge within a system. It's a much deeper thing. I certainly use the term dry quite a lot when I talk to people, do code reviews and whatever. But we must also recognize that this is not some kind of absolute, even though the problem that we have is that it is phrased as an absolute. So it's kind of cute, but that may be its downfall. So in 97 Things Every Programmer Should Know, the book that Felix referred to in the intro, there was a lovely piece by Udi Dahan, Beware the Share. Now, I have a piece in there on, Don't Repeat Yourself. I also have a piece on Beware the Share. In fact, I have a number of pieces I included in that book, pieces that were counterbalances, that were opposites to one another. And a similar thing last year with Trisha G, we published 97 Things Every Java Programmer Should Know. We actually included a number of items that you might say, well, hang on, don't these contradict each other? And to which the answer is yes, because it depends. We are not giving you the answer. We want to show you the shape of the space across which you must have your own judgment and across which you must reason. So Beware the Share is the counterbalance. Udi describes his first job after university. As I worked through my first feature, I took extra care to put in place everything I had learned: commenting, logging, pulling out shared code into libraries where possible, the works. The code review I had felt so ready for came as a rude awakening. Reuse was frowned upon. How could this be? Throughout college, reuse was held up as the epitome of quality software engineering. All the articles I had read, the textbooks, the seasoned software professionals who taught me, was it all wrong? It turns out I was missing something critical: context. The fact that two wildly different parts of the system performed some logic in the same way meant less than I thought. Up until I had pulled out those libraries of shared code, those parts were not dependent on each other. Each could evolve independently. In other words, although we often think of coupling and cohesion as trading off against one another, actually the real challenge here is duplication versus coupling. There's a trade-off, there's a tension, there are forces that pull both ways. And this is probably how we need to think about the guidance that we offer people. If you look through things like the Zen of Python, if you're not familiar with the Zen of Python, go Google the Zen of Python. There's a couple of things there that are very Python specific, but there's a number of things in there that are offered in pairs. They are balanced pairs of advice. In other words, they say, yeah, here's your default, but here's the counterbalance. In other words, we should appreciate all knowledge as that, rather than more of this is necessarily better. So sometimes we encounter things that aren't directives. They tell you to do something. Sometimes these get reframed as principles. I'm not always comfortable with that idea of principles, because sometimes there's an ethical, although there are ethical questions that we need to answer in the realm of software. I don't wish to impose a moral judgment on somebody's use of a coding feature. Sometimes there is a sort of a question there, but there's also a universality about principles, that they, in one sense, they are context-free. They are always things. So I kind of have a strong background in patterns. And for me, one of the most important things about patterns is the bit that many people miss. A lot of people look at patterns as being like a shopping list of design ideas, or they completely misunderstand them. And, oh, yeah, you mean the book that was written in 1994? No, I don't mean the book that was written in 1994. I mean patterns. Felix mentioned that he'd encountered my name in the Poser books. In Poser 4, we documented 114 patterns. For those that are pattern spotters, the 115th would have been Singleton, but I took it out of the book. But we documented 114 and referred to another 300. In other words, this is a space. What we're trying to do here is nothing less ambitious and nothing more ambitious than simply map out knowledge, give regions of knowledge names so that we can talk about them, so we can exchange them, so we can have communication about what we are trying to build. But more importantly is that these are not directives. What they are is contextual pieces of advice. If you are outside that context, here's a thing that works in this context. If you do it outside this context, guess what? It might not be a good thing. That's kind of built in. And that is one of the things I find most powerful and yet most people overlook. And this really is integrated with the whole patterns model of thinking. This is the way. The Timeless Way of Building by Christopher Alexander is one of the books that he wrote in the 1970s. It's a glorious piece of writing. It's a wonderfully aesthetic book. It certainly rings true of its time. There's a real nice 1970s vibe to it. But actually, it's a wonderful aesthetic and thinking as well. What he's looking for is to understand the way that designs of our built environment work. And this is what inspired Kent Beck and Ward Cunningham in the late 80s to bring this idea of patterns into software. They were the originators of patterns in the software world. 1987, if I remember correctly. It is this idea of contextual thinking. And that's what Christopher Alexander was really trying to emphasize, is this idea of there is a context in which arise conflicting forces. In the software world, we just tend to simplify this and call it the problem, okay? Context gives rise to the problem. And he says, and we respond with a configuration. The software world, we tend to talk about solution. We also tend to put in a lot more emphasis on the idea of consequences, if you like, the resulting context. Now that you have applied this approach, whether it is a tiny programming idea, or if it is something much broader with architectural significance, it applies at all levels. There is the idea that it has consequences. Maybe it uses more memory, less memory, maybe it's more complex to maintain, and so on. In other words, let's understand, let's be very honest about the consequences so that we can make a reasoned judgment But this is not unique to patterns. This is actually broadly about design. This is actually about design. So sometimes, although I say I learned this from the patterns world, we actually learn about design. Design is a kind of like a structured response, which is going to influence our code. Good. I'm glad that people are picking up on the Mandalorian references. Well done. Felix has made the observation that there are no patterns in the, an observation by Jim Kaplan, who likes to stir a little bit of interest every now and then, that there are no actual design patterns in the Goff book. Now, he said this in the late 1990s, and I took him to task over it. I said, actually, I think you're wrong. I think there are about 100, and I pointed them out to him. So he likes to have a controversial thing, but do keep in mind, mostly it's not right. There's actually a lot more depth in that book. The problem is you have to look for it. It's not necessarily stated up front. So let's talk about the fact that this morning, had I actually gone into the hotel, walked to the centre of Bristol, 25 minutes walk away to give this keynote, I would have got wet. The sun has just come out at this point. There is this observation that there's no such thing as bad weather, only unsuitable clothing. This has been, I tried to find a definitive source for it. It turns out everybody said this at one time or another in the last century or two. So I can't give you a definitive source for it. So why am I putting this here? Because it's to do with context. What we're doing is we're saying that you have to understand the context in which something works. So let's talk a little bit about, I'm going to pick a context. Let's work through an example, a sort of series of examples and thoughts. Let me pick on the world of multi-threading. And one of those things that comes up every now and then, people say, oh, we need to make this class thread safe. And it's like, what does that mean? I remember one of my most frustrating consultancy calls years ago when I had a couple of architects, can you make any recommendations for thread-safe libraries? And I said, well, what do you mean by thread-safe? And they said, well, thread-safe. I said, well, hang on, what's your threading model for your system? What's your architectural approach? What approach have you taken? Oh, we haven't. So hang on, you're hoping a library will cause magic. Spoiler alert, libraries do not cause magic. They do not cause magic to happen. Magic is not a real thing, okay? At best, magic is mostly deception and boundaries and playing with how people reason. It's a bit like undefined behavior. There's no such thing as undefined behavior. I will get to that. So what we have is this issue that people aren't really sure what they mean when they say thread safe. These guys, it turns out that what had happened is they said, oh, the developers just keep using threads. And so it's a case of like, yeah, but that's an architectural decision. What you're describing for your program is threading is not an implementation detail that you get from a library. Threading is an architectural decision, like whether or not your code is time-driven, event-driven, whether you use a different form of concurrency or whatever. What you're dealing with is the fabric of space and time for your code. That is not a detail. That is the nature and depth of how your code is, the physics of your system. So for many people, they think, oh, thread safe, that means mutex. I'm going to borrow from David Butenhoff, one of the originators of pthreads. Perhaps we should have called mutex bottleneck. Perhaps people would use it a lot less then. It's a very honest description of what it is. If you're trying to use threads for performance, why are you using mutexes? The whole point of mutexes is they prevent threading. That's their goal. Their job is to eliminate performance and threading. Now, if we're in the C++ world, we would use a scope lock to try and keep things nice and tidy. If we're in the Java world, we use something like synchronized methods, synchronized blocks. Various languages have various constructs for dealing with this. Now, in the Java world in the mid-1990s, they followed what a lot of people were thinking of as being thread safe. They said, "Oh, right, we're going to have threads, so all of our libraries should be thread safe." And they had a thing called string buffer, which allows you to concatenate a string, and all of its methods are synchronized. Okay, so therefore it is thread safe. But there's another thing. There's a string. A string is also thread safe, and it has no synchronization whatsoever. It's at the exact opposite end of the spectrum because it is perfectly immutable. So they are both thread safe. One, because it locks the hell out of everything. One, because it is utterly lockless. Okay. It does not need locks. You know, this observation, my favorite title about immutability, piece by Pat Helland, I think 2015, Communications of the ACM, immutability changes everything. The point here is that there are two different ways here, at least. But I'm going to turn this one on its head. There's no such thing as thread-unsafe code, only unsuitable threading. The problem with string buffer is that actually it doesn't make sense. What happened is that the designers of this and the designers of many threaded libraries were designing without a context, without understanding the context. They were not solving an actual design problem. They were solving an imagined problem. And what do I mean by imagined problem? Well, here's the problem they were solving. What you are going to do is concatenate a string that is shared between threads. That's actually not a problem. I would actually say, what the hell do you think you're doing? Why are you designing for that? That's a stupid case. If you want people to solve that case, let them write their own wrapper. That is not even, that's not just not a general case. It is probably a very, very edge case. Why are we designing for that? That's not really a problem. Most people are not doing this. You are causing people to pay for something that they are not using. And you've got unnecessary generality. That's the problem. Sometimes when people will design without a context and without real code in mind, they end up with massively general code with inappropriate complexity. You can look at things like the C++ standard library for lots of examples of that. So in the Java world, they responded in the way that the .NET world did. They added string builder. They didn't deprecate string buffer, but string builder is the way these days. String builder is thread safe. Now, some people say, well, no, Kevlin, it doesn't have synchronized things, and yet it is mutable. It isn't thread safe. No, it is thread safe. You're supposed to use the object in one thread. Why the hell are you sharing it across threads? That's a stupid thing to do. Most code that people write is actually thread safe. It's just that you're only supposed to use it in one thread at a time. That's the point. People have not understood the context. And when they say thread safe, if somebody says this is thread safe and they don't define a context, they probably don't really know what they're talking about. They have not clarified their thinking to the level that we can say, oh yeah. So most code that does not use synchronization and is mutable is actually thread safe. For the threading context in which it is intended, it is absolutely safe. Now, we might pick on some other examples. We might say, well, what if I'm using static? What if I'm using static in my code? You know, maybe I have, I've got global state, whether it's hidden inside a function or at a class level or whatever. It's static. There can be only one at this point. And so therefore, if I have multiple threads running through this, then it's not safe. I'm going to say, you know what? Code that uses static is perfectly safe. Let's pick an example from C. So here, an actual example is given in the C standard that uses static. So ask time, which is not recommended, by the way. This is not a recommendation. What we see here is that this is code that uses static. In other words, it formats a string. There's a few functions like this in old C that format a string into a static space. The statics above are fine. They're static consts. They're perfectly immutable. That's fine. This is good. This is the static of interest. This is clearly not immutable. We've got this one thing, and then we write into it, and then we return it. The next caller to this will erase and overwrite that. This is thread safe. But how can it be thread safe? Yeah, if you only ever pass one thread through it, it is perfectly safe. If I only ever have one thread dedicated to such functions, those are safe. That, by the way, is how you wrap up such libraries. So by acknowledging that, this is thread safe. It has a particular context. In a program with a single thread, it is automatically safe. Oh, you might get other surprises, and there's a bunch of other reasons you don't want to do this, but you can't level the accusation of thread unsafety at it. This is thread safe for one thread, okay? Classes that do not have synchronization but have mutability are thread safe if the objects of their instances are used in one thread. What about the thread safety of gets? Gets was removed from C11. Why was it removed from C11? Because, hey, guess what? I get to get a string. I get to pull a string from the IO without any boundary checking. I get to do buffer overflow. This is a great cause of buffer overflow. So you can see there's no n. I don't pass a boundary in. I don't say, guess what? This string, it has an end. You know, here's the pointer to the beginning of a bit of memory, and it goes on Until when? Who knows? People ended up using it, funnily enough, partly because of mistaken symmetry, because there's puts, which is perfectly safe, although relatively pointless as a function, and puts and gets. There's a kind of false symmetry there that we kind of get drawn into. And so it's like people ended up using that. So here's a piece of code. We've got chart, we're going to prompt, what is your full name? And then we expect people to type in. And if I type my full name in, it turns out that I will run off the end. I will get a buffer overflow. Now, some people will say, but this is undefined behavior. You're damn right, but there's no such thing as undefined behavior in the real world. Undefined behavior is an artifact of the limits that we place on a specification. You cannot observe undefined behavior. That's not a thing. Undefined behavior is an artifact of a boundary that we have placed. It is undefined by the C standard, but in the real world, it really will have behavior, because otherwise, there's a whole lot of people who do security hacking who will tell you, oh, trust me, the behavior is incredibly well defined with respect to a given context. I can tell you what's going to happen. That is the point of the security exploit. So undefined behavior, sometimes people hide behind it as if the standard was the one true answer. No, the thing in the world is the one true answer. A specification is a way to get us there. It's a way that we use to manage the complexity of the world. We place a boundary so that we can reason on it, but don't confuse the map for the territory. I find a lot of people who talk about undefined behavior confuse these two. Yeah, you know, it's one of those things. You know, at this point, if you wanted to say, Kevlin, what's the weather? I guess I could go and look at a website, or I could look out the window. That's the real world is doing that. And if the website disagrees with the real world, you know what? I'm going to say that the website's wrong. So here's this point, that our programs exist in a context. Now, how do we reason about these? It turns out that there are a number of different things and a number of different levels. This is a model that I came across. Yeah, Bobby tables, by the way, I removed those slides. I had those slides in the deck, but I was going to talk about Bobby tables. If you do not know what Bobby tables is, go and look, Google Little Bobby tables. It's an XKCD cartoon. So I want to pick on something from 1980, a rather useful, a wonderful paper by Maya Manny Lehman, Programs, Life Cycles and Laws of Software Evolution. And it's over 40 years old and yet still has a great deal to teach us. What I found a few years ago when I revisited this was a model for thinking about our code and the consequences of our code. And it's the relationship to our knowledge that I had completely forgotten about. And I found incredibly useful in terms of thinking about how we work with things. So S programs, P programs, E programs. So thank you, Magdalena, for posting the XKCD link. What is an S program? S code or S systems, programs whose function is normally defined by and derivable from a specification. You know, this is the stuff of sorting algorithms. Okay, in other words, I can tell you straight out what I'm expecting. I can bound it. I can do this formally. I can do it verbally. I can give you concrete examples. I can write test code. In other words, we can understand it, and from that, I can probably come up with a number of candidate ways to build these things. You know, it's not that you can, when we say formally derivable, we don't mean that there's like a one button that you push and magically you end up with the 5th generation computing program and you end up with code being dropped out that's perfectly satisfies the spec. That's not what we're saying here. What we're saying is that idea is that there is a very clear relationship, and that with the right context of knowledge and experience, you're able to go, oh, yep, this fits here, and that's it. This applies to things like accountancy systems as well. The rules of accountancy, although seemingly arbitrary to mere mortals, are actually rules. It's a defined system. So this is not just about toy algorithms. The great thing about S programs is that we can reason about them, or S code. If I can break something down into S code, then I can think about it, reason about it. It doesn't mean I'm going to get it right. It just means that the boundaries with which I'm able to work with are, I could get it right. There is a possibility. And so, as I mentioned, algorithms, I'm going to cite John Bentley, who wrote a column for Communications of the ACM, Programming Pearls, and collected many of his columns into a couple of books, Programming Pearls and More Programming Pearls, and there was a second edition of Programming Pearls at the end of the 90s. And there's a kind of glorious irony, because he's got this piece here called Writing Correct Programs. And John Bentley talked about binary search, and he ended up creating a binary search that was, and he ended up writing a proof for it. And one of his students was Josh Block, who used to work for Sun and was the principal creator of the Java Collections API. And Josh used the algorithms he'd learned from Bentley, and so here is a binary search. There is only one problem. There is a bug. There is a bug in this code. And it turns out that pretty much every piece of code that ever borrowed from that binary search and sorting algorithm work that John Bentley did had this bug as well. By the way, it was proven correct, remember? This is why we must understand the consequences of our assumptions. The assumption here is that when you add two numbers together and you divide them by 2, you get the average. You know what? That's what you're taught at school. That's what you learn in maths. That is what every scientific discipline is kind of based on. And by the way, when I'm talking about maths, unless I'm talking about maths, I am referring to the maths that everybody generally works with, not the mathematician stuff. You know, if you start talking category theory, no, that's not maths for most people. Their experience, if you've done engineering, if you've done a science, your daily experience is really in the number crunching space, and that numbers behave kind of in ways that you would expect them to behave. And when you add two numbers and divide them by 2, the only thing you have to worry about here is integer rounding. except that integers and ints are not integers. It's one of those things, by the way, I always kind of think is an accidental side effect of our desire to abbreviate the use of the word int rather than integer. Programming languages used to use the full word integer, and then Algol 68 came along and everybody abbreviated everything. The thing is that int is a truncation, so I think it's actually quite reasonable. It turns out that when you add these two numbers, you get a wraparound. And so therefore, for very large numbers, the midpoint is actually not the midpoint between the two large numbers. It actually turns out to be hugely negative. Why did nobody detect this in the 80s? Well, because if you are working on 32-bit ints, that means you have to have incredibly large arrays, which we wouldn't have had. These arrays are now what we consider to be trivial. So it turns out that people simply had not hit those limits. If you want to do it, you can do it like this. Okay, that's a way of doing it. And then, so Josh points this one out, and then he points this one out. So this is an unsigned shift. And he puts this one in there, but his comment, probably faster and arguably as clear. Yeah, really? Okay. So it's a lovely book, beautiful code. Alberto Savoia, who has written a lot of wonderful things on unit testing, he actually wrote a piece on exactly the Bentley bug and how to test for it and how to extract a midpoint and test for it. And one of the things is in analyzing, he made a comment about Josh's unsigned shift. Probably faster, but maybe obscure to most Java developers, including me. In other words, if you think that that is intuitive, there's something wrong with you, okay? And I'm sure you're lovely, but there's still something wrong with you. The point here is that no, if I want to find the midpoint, doing a right shift is not even remotely a natural way of doing it, unless you write the kind of code that means that you program on your own. But there's another point here, another assumption. And this one, I can quote from John Bentley's other book. And this is the late 1980s when Guy Steele said this. If the programmer can simulate a construct faster than the compiler can implement the construct itself, then the compiler writer has blown it badly. This wisdom is not new. This is over 30 years old. So please do not do the job of the compiler. Okay, do not micro-optimize like that. Let the compiler writers do it. And if you find the code is non-optimal, guess what? You have a way of feeding back to them. That's wonderful. And you have just increased the knowledge of the world by making that contribution. So the other thing here is that many of the things that we experience as failure are in S systems. It turns out a lot of our code, no matter how complex it is, conforms to this kind of S idea. And this paper by Wiener et al. From 2014, I love the title because it tells you everything you need to know. It does what it says on the tin. Simple testing can prevent most critical failures. And they analyzed a number of open source distributed data intensive systems. There's a lot of data out there. One of the most interesting conclusions in the paper a majority of the production failures can be reproduced by a unit test, like 3/4. This is important. It doesn't mean that we could have found those necessarily, because we need to figure out what our assumptions are. I'm going to explore assumptions in a moment. It doesn't mean you could have found it in advance, but once you have found it, you can know it and you can demonstrate it. And a lot of people go, oh, we can't test for that. We can't test for that. It's like, yes, you can. Or rather, there's a 3/4 chance you can. Funnily enough, 3/4 or 75% is roughly the probability that when you look out the window, this time tomorrow, the weather that you're seeing will be the weather this time that you're seeing now. So basically, if you are in the business of trying to forecast the weather, all that computing power, all of those models, you have to beat the 75% mark, because anybody can just look out the window and go, yep, that's my forecast for tomorrow. 75% chance is what I'm seeing at the moment. You've got to do better than that. So those models have got a lot of hard work to do. However, the point here is that once you've done that, is that you've got this idea of being able to absorb the knowledge. You can use that in future code reviews, as somebody's pointed out. You can use that in a test suite. You can capture that knowledge. By the way, there is a question, and I forgot to say, I didn't conclude on what I should have said about gets and its thread safety. Is gets, the gets function, is it thread safe? Yes, it is. It is thread safe for 0 threads. Okay, so in other words, if no threads pass through it, it's perfectly safe. Which answers the question that I've just seen. Is it possible for something to be thread unsafe in the context of a single thread? Yes, gets. So therefore, we have this idea of 0, 1, 1 per thread, many. Okay, and that gives us this idea. Thread safety is a set of degrees and context dependency there. So thank you for asking that question. Josh says, the general lesson I take away from this bug is humility. It is hard to write even the smallest piece of code correctly, and our whole world runs on big, complex pieces of code. We should always approach this with humility, the same humility as a novice, that when we work with a system, if we are new to it, then we are a novice, no matter what our years of experience. That when we offer a piece of code, and it is the first time we have created that code, we are novices in that particular domain. This is the first time I have written this. You know what? The second time I write it, it might be better. But I also understand that my knowledge will be incomplete. There's always more that I can learn. That is the way we should approach every single task. And that's quite difficult. But let's move on to P. P programs are interesting. They are based on acceptability. In other words, I can't tell you immediately what I think is right, but I can kind of tell you when I see it. It's kind of, when I put it in an environment and I kind of say, well, I'm not only adjusting the algorithm, so to speak, I'm also I'm not just making up the code, I'm also kind of making up the requirements against which I'm going to test. In other words, both sides are kind of variable. The problem with S systems is not that we cannot know, it's that sometimes we just don't have complete knowledge, but certain things are kind of a priori we can figure out. There is a set of rules and expectations that we can say to do with sorting, accounting systems and things like that. I can tell you the right answer and the wrong answer. The fact that I may not have known that in advance, that's a limit of my knowledge. But these systems are interesting because they're much more negotiable. We have to find a procedure or a practice for determining, yeah, what do we mean by right? So what do we mean by what we want to do and what do we mean by right? And how are we going to implement? You get to choose all of the parts, which is quite dangerous when a programmer gets to choose the outcome. And what's interesting is that this category didn't mean a whole lot in 1980, or rather it had a few examples, but these days this is machine learning. So this is your machine learning system. Yep, you pour the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? You just stir the pile until they start looking right. That is a P system. And much as the media loves to use the word algorithm, there really is nothing sinister about the algorithms and machine learning. The problem we have with machine learning is not here. As Mike Lukides makes the observation, AI is characterized by output that isn't strictly dependent on the input or on the algorithm. It depends critically on a training process. And training differentiates AI from traditional software applications and data. Or let me put it another way. Sure, the input has some impact, but that's not the real issue. Sure, the algorithm and your choice of algorithm, that is something you need to design and work on. It's the fact that most of what comes out of a machine learning system is based on a configuration. The configuration typically has millions of parameters and is completely human unreadable, and no human was involved in reviewing it. That is the problem. So if somebody says, here's a big config file, it's kind of like, oh, okay, that is your system. It's not the algorithm. It is actually the data that is driving it. Now, sometimes people have been looking, there's a thing that, there's an interesting idea that I've seen crop up every now and then, which is this idea of explainable AI. And there was a good critique of this. Explanations must be wrong. They cannot have perfect fidelity with respect to the original model. If the explanation was completely faithful to what the original model computes, then it would equal the original model. And you could just throw all that stuff away and replace it. That's actually not a bad way of using machine learning. It's just that that's not the way it's used. So in other words, if I have a model that is perfectly accurate for to describe the behavior of the system, then I should replace the system with that model because they are functionally equivalent. The point is that we don't actually know because we didn't really know what the question was that we asked. So we didn't really know what the question, we're not entirely sure of the answer. That doesn't mean it's not useful. It's incredibly powerful. And that's a different statement. Sometimes it's very useful. We're just looking for patterns in data, which most people will tell you, by the way, is bad science. Honestly, most machine learning is just number crunching. It's surprisingly dull. And a lot of what people do with it is just bad science, unfortunately. And we have this problem of an assumption that is built in. If we are building on the past, then how do we deal with change? You can end up with patterns that reflect the past. If those patterns are used to make decisions that affect people's lives, you end up with an unacceptable discrimination. Because we cannot see that, you cannot find the bit of the lines of code, the causal explanation. And this is important because this is about a model of knowledge. Are we able to reason about stuff? Almost all the coding conventions that we have established, all the debates we have about coding practices, they are about our ability as developers to reason through things. We favor one style over another because it is easier to read or easier to reason about. And then along comes something that says, oh, by the way, the one thing you can't do with this is reason about it. But guess what? This is the future. We need to be a little more cautious about that. Now, if we left that to its own devices, that'd be fine. The problem is this takes us to the next category. E-programs. Programs that mechanize a human or societal activity. Again, back in 1980, there weren't a lot of examples of this. And what we're saying, the program has become a part of the world it models. It is embedded in it. The example that Layman chooses is an air traffic control system, where the output of an air traffic control system is used by an air traffic controller to give advice to an aircraft that then responds and is now its new data, its new position and vector is now picked up by the system, and in other words, we have now got a loop. But we see this everywhere now. In 2021, we see this absolutely everywhere. We have these feedback loops all over the place, and we see it in the realm of politics. We see it in the realm of commerce. My favorite simple example, I've used this once before at an ACCU conference, but I do like it, so I'm going to feature it. It's a kind of nice microcosm just to demonstrate the surprising behavior that we can get. So this is from 2011. And this is on Amazon, but this is not Amazon's product. This is Amazon as a marketplace for separate vendors. And the making of a fly, the genetics of animal design. Apparently, this is a really awesome book. If you're a geneticist, geneticists did tell me when I showed them this slide, they said, oh, yep, that's kind of a standard text. So I want you to look at the price, US dollars. 1.7 million. I'm sure it's good, but I'm sure it's not that good. But hey, guess what? One of the vendors is offering it for 2.2 million, so 1.7 is looking pretty good. Or you can buy it, and that's the price new, or you can buy it secondhand for $35. I'm not an economist, but I think I know which way I'm going. What's going on here? So this analysis by Michael Eisner, he kind of looks at this and he says, look, I track the prices over successive days. What is interesting is what is interesting here is when we look at those numbers, those ratios. We have two vendors, Profnath and Book. Consistently, Profnath is undercutting the algorithm that is used by Profnath. Is they will undercut the lowest other price out there. This is an S program. Book, however, oh, by the way, Profnath have the book. Book don't have the book. Their strategy is they will they will have a 27% markup or 28% markup on a book. And when you buy it from them, they go and buy it from elsewhere and get this nice hefty markup. Nice. This is also an S program. Guess what happens when we take two things that are very well specified and you put them together? You end up, well, it topped out around just under 24 million before the plug was pulled. Now, the point here is that the idea is that we've ended up with this kind of feedback behavior, and the world was very small and it was very simple, and we can see that. And I believe Amazon and others now always check for these cases. But that's the point, is that all they've done is they've just checked a thing that has, that has now been understood, but somebody had to stumble over that assumption, over that brick. Before finding that. The question you should ask is not that we've patched this, is what other holes do we currently have? But that should also remind us, when you're designing something, just as with the threading question, you need to look one step out. Where is this being used? What is the context that provides this with meaning or may disrupt the meaning that I have assumed? Of course, we will not always be able to design to fully understand a larger context, but if we make no effort, you're guaranteed you won't get it right. If we make some effort, we'll get some of it right. So when it comes to sources of wisdom and knowledge, Douglas Adams is a hugely rich seam. And he observed, he said, there is a theory which states that if ever anyone discovers exactly what the universe is for and why it is here, it will instantly disappear and be replaced by something even more bizarre and inexplicable. There is another theory which states that this has already happened. In fact, for many of us, we kind of believe that the world forked in 2016. So there was a whole load of stuff that happened in 2016. The Brexit vote was an interesting one. I use interesting in bold and wingdings there. But what is interesting is that at that point, the pound was incredibly volatile, well, volatile mostly in a downward direction. But there was a rather interesting episode in October of 2016 when the pound crashed, falling off a cliff style. And you're looking at that going, whoa, what happened there? That's, indeed, there was a lot of volatility politically and in the markets, but look at the time frame. That's a matter of minutes. Humans cannot be this stupid this fast. Okay, that is not one of our skills. We have an immense amount of wisdom and also an immense capacity for stupidity, but we're just not that fast with stupid. The point here is that as a safety systems expert came up with Wiener's laws for aircraft safety, observes digital devices tune out small errors while creating opportunities for large errors. That is algorithmic trading. That is the Amazon problem, but now in a much more open system where we have limits on what we can know and genuinely know. We still don't know the full cause of that flash crash. So when we look at this model, we can actually see that there are some interesting things here, that when we look at S&P, we're dealing with closed universes and closed domains. But when we deal with E, it is open, it is unbounded. When we deal with S, it is defined. When we deal with P and E, they are undefined, not the undefined I was talking earlier. I mean that it is not a priori defined what we're going to expect. But the difference with P is it is definable. This is the whole thing. We may not know everything, but we can know enough. And that's what we mean by this one. So this is kind of taking us into the realms of epistemology and philosophy, which is quite appropriate because effectively programming is an act of applied philosophy. And the great Grace Hopper basically invented the compiler and was also happened to be a rear admiral in the US Navy, a woman of incredible achievement and great wisdom and perennial wisdom. She made this observation: to me, programming is more than an important practical art. It is also a gigantic undertaking in the foundations of knowledge. And there was a useful model published in Comms of the ACM in 2000 by Philip Armour, the 5 orders of ignorance. Level 0, so nice, he counts from 0. We have a lack of ignorance. 1, lack of knowledge, lack of awareness, lack of process, meta-ignorance. What do these categories mean? Well, first of all, I'll start with number 4. Meta-ignorance means you don't know about the 5 orders of ignorance. We're going to solve that one, so we can take that one off the table. Let's replace it with some slightly more familiar plays with words. There's the known knowns. This is what I know. Okay. The known unknowns. Here are the things that I can list that I know I don't know, that we're about to deal with in the code. Yeah, I don't know. I know I don't know this library. I know I don't know this domain. No, I don't know the customer. I've not had a relation. I've not worked with this team before. In other words, we can go through and actually say there's a bunch of things that, honestly, I know that I don't know, and I'm not surprised by that. I'd like to say that we're good at this, but actually we're not. Many people cling to that. Expert beginners will not acknowledge this. This is the first bit. The first act of humility is to recognize this and also upgrade it. As humans, we have an unfortunate bias. It's an interesting feedback cycle. If I don't know something, if I know that I don't know something, then that's okay, because it's probably not important, because if it were important, I would know it. Yeah, see, there's a beautiful little loop there. So we need to remember to upgrade the fact that you don't know something, give it the same seat at the table as the stuff that we do know. And we might think, okay, this is how we're going to plan. Yeah, but now it gets exciting. Unknown unknowns. It turns out most of what we encounter in software development is the stuff that we didn't know we didn't know. That's where most of the surprises start hitting us, the bugs and things like that. We can't, if somebody says, oh, could you estimate how long it's going to take you to fix the bugs that you're going to create next week? I can't. I don't know, or the bugs you've just put into the system. How do you know I put a bug in? Well, I don't know, but you must have done. Well, I don't know what the bug is. You haven't been able to tell me. And even if you do tell me what the bug, how it manifests itself, that doesn't mean I automatically know how to fix it. I can't say, it took me 5 minutes to put the bug in, it'll take me 5 minutes to take out. It just doesn't work like that. There are people who have taken months to try and find bugs. In fact, I know of cases where people have spent whole seasons finding bugs and even given up on finding a bug and rewritten the system because it was easier. So here's where the unknown unknowns start hitting us. That's where our assumptions live. And then there are the unknowable unknowns. And what do we mean by that? It's not that they are not eventually unknowable. What we mean is we do not have a process for finding out the answer to that question. And that not only will the question not occur to us, but we don't actually have a process for finding it out. If you ask everybody their holiday plans in 2019 for 2020, guess what? Nobody had pandemic on the list. Okay, so the point is there is no process for finding that out. You could not have done any research that would have given you that answer, because it is not knowable until you arrived at it. The only thing that makes it knowable is time. So, which leaves us with the Socratic paradox. I know that I know nothing. I mean, Socrates was the original humble programmer. He was the original Jon Snow, but he didn't have to be told that he knew nothing. He had this awareness. Well, we think it was Socrates. There's evidence that it might not have been. So we see this challenge of knowledge, that much of what we do and how we frame things is based on the assumption, first of all, I like the S-system model. We need to make more of our code look S-system-like. We need to acknowledge that. But we also need to recognize that actually in deployment, most things, and in connection, they become much more complex. Their dependencies get beyond the point that it's not just a bit difficult for a human to know, it's actually not possible. So this kind of takes us to ultra large scale systems. And ultra large scale systems, there's a report done in the 2000s. One of my co-authors, Doug Schmidt, was involved in creating that report on ultra large scale systems. And they have a number of priorities. If you like, these are kind of like the core concept that by definitionally, in other words, this is not a lack of ability, this is by definition. These systems are unknowable, decentralized, evolving, heterogeneous, and failing. The key thing there is unknowable and failing from the point of view of many people is that idea of like, yeah, but I want it to work, whatever, doesn't matter. It is also unknowable. That is a priori statement about the system. This also gives us the fact that we are now going to be exposed to Lamport's observation that a distributed system is one in which the failure of a computer you didn't even know existed can render your own computer unusable. I noticed a while back when there were fires raging in California that my publisher suddenly had a little bit of had a location transparency issue, and when I went online, it's like, oh, okay. Somebody else had experienced this. So this is kind of an interesting one. This also gives us the idea that the knowledge, the state of a system, by definition, is a distributed system is, as I said, it's a feature that it's not in a consistent state, that its state cannot be necessarily knowable at a point in time. The problem is that sometimes people let this leak over into their code. I often see cases either on my mobile or on web apps where something will say, hey, you've got 5 items in your queue, and then I'm looking at the screen and there are 4 items. And somebody will normally say, oh, well, that's an eventual consistency thing. No, it isn't. We have a name for that. It's just called badly reviewed code. Because in the client, I have 2 numbers. I have 5 and I have 4. The client has to make a decision. What am I showing you? Well, I'm showing you 4 things. So therefore, the correct number of messages at this point that I'm showing you is 4. It is not 5. If I got that data via another source, then we have an inconsistency. But I have to choose one answer. In other words, this is a client-side problem. It's nothing to do with distributed systems. So I do wish that people like, I know, Google, Facebook, and all the others would learn how to write client-side code. I think it would really help us. It doesn't matter if the nature of the system is eventually consistent and ultimately unknowable. What should appear on the client, which is located in one location, can be defined in terms of a bounded and knowable behavior. But when we are looking out to the network, this question of consistency, sometimes known as Brewer's theorem, after Eric Brewer, who kind of coined it in the late 90s. CAP theorem is probably its better name. I think he described it originally as a principle, then he offered it as a conjecture, and then somebody actually proved it. So it genuinely is a theorem. It's not just an abuse of the word theorem. Is based on the idea a system can have consistency, availability, partition tolerance. Okay, let's clarify the terminology. Consistency here, what we mean by consistency is we're saying something relatively simple. Whenever you ask for behavior, you will get, particularly via request of value, I will get the most recent updated value, or I will get an error. I will be told, I'm sorry, I don't have this available. Availability is the idea that every request, every operation will have a response that won't be an error response, even if it's the wrong answer, or rather, it's the most recent answer we had. But there may be a different answer elsewhere. Partition tolerance is that a partition is a useful euphemism for network failure. In other words, your network has become partitioned. You thought it was one network, but now you have 2. In other words, we lose messages across the network, partitioning in space and time in that sense. There's an observation here from Dom. There's nothing new in computing since the 1970s. I did a talk entitled 1968 a couple of years ago, so it's not representable in the Unix correctly in Unix time, but it's not far off. So there is an interesting thought here that what we've got is that we can have, you are allowed, you can have any 2. You can't have all 3. That's what we're basically saying. That becomes, you can have consistency and availability, and you can have, let's see, you can have that. You can have, in other words, you can be consistent and available, but not partition tolerant. It turns out this is a false dichotomy, because if you're dealing with a distributed system, honestly, you don't have a choice about the partition tolerance. You do have to, for anything meaningful, you have to be partition tolerant, because you don't get to control whether or not the network works. When your network becomes a not work or a niet work, that's not a decision you can take. That's not a coding thing that you can do. You have control over consistency and availability. You don't get control over whether or not the network works. However, what is interesting is in the limiting case for you are programming locally in one node, actually you can make this claim. So there is a reason to include this, but it's not necessarily useful if you genuinely are working with distributed systems. So you've got a choice here. You can be consistent and partially tolerant, or available and partially tolerant. You cannot have all 3. This is kind of like a Heisenberg uncertainty principle. Somebody mentioned quantum mechanics in the chat. Here it is. It's the classic case. Heisenberg gets pulled over by a cop. You were speeding. Yes. And do you know how fast you're going? Yes, but I have absolutely no idea where I am. You cannot know your position and your momentum with high fidelity at the same time. There's a trade-off between the 2, and that's kind of woven into the universe. In other words, What we get, we demand rigidly defined areas of doubt and uncertainty, and it turns out that we've been given that in spades. The beginning of the 20th century just knocked away all of the certainties of Victorian physics. Everybody thought the end of physics was in sight. Interestingly enough, I saw a headline this morning, something, oh, the end of physics, question mark. Betteridge's law of headlines. Is this the end of physics? Betteridge's law of headlines is if a headline asks a question, the answer is probably no. We had this over 100 years ago. It's not true now either. It turns out everybody had everything wrapped up. Then quantum mechanics came along with its uncertainty, and then it dropped out of Einstein's equations that, you know what, there are these points in the universe, there are these areas in the universe that are, well, black holes. But here's another thing I want to go back to. Remember I said there's no such thing as undefined behavior. There's just behavior that we have chosen not to define. You cannot observe undefined behavior. It's not a behavior. In the real world, there's no such thing. Similarly, people like to describe black holes. So this is in this way. So this is the Event Horizon Telescope's image taken in 2017, released to the public, processed and released to the public in 2019. 6 billion solar masses. Absolutely awesome. It's the shadow of a black hole. I mean, it's one of the coolest images of the 2010s. But sometimes people say, oh, beyond the event horizon, the laws of physics breaks down. No, they don't. They really do not. The laws of physics are just fine. We don't know what happens, but that's a limit on our knowledge. That's not a statement about the universe. We've confused the map with the territory again. So there is this interesting thing that right at the beginning of the 20th century, other things were falling apart. Kurt Gödel really messed things up with this paper, the English translation of it, on formally undecidable propositions of Principia Mathematica and related systems. Because in 1911, Bertrand Russell and Alfred North Whitehead published Principia Mathematica, which is basically trying to prove everything, mathematically. Mathematics is consistent, it's solid, it makes sense, everything can be proven. 1931, Kurt Gödel came along, although Adrian Collier's called it incompleteness theorems, actually two theorems, incompleteness theorems, shattered the dream, showing that for any consistent axiomatic system, there will always be theorems that cannot be proven within the system. One of the most important things to notice here is and related systems. That's why in software it's important for us, because it's related systems. We can turn everything that we've got into a numbered system. Yeah, that's what happens when the compiler gets its sticky paws on your code. Okay, that's what happens all the way down. It doesn't matter if you've got virtualization or whatever. Somewhere down here, before we hit the electrons, we've turned everything into numbers, and we've ascribed those numbers meaning. So Gödel, Escher, Bach was really my wonderful book. It was one of my kind of like real introductions to like how weird all this stuff really is and the limits of knowability. And Hofstadter observed his observation, all consistent axiomatic formulations of number theory include undecidable propositions. Let's just look at that undecidability aspect, that idea of undecidable. That's kind of a little bit interesting because, again, this is a limiting thing. It's a boundary on our knowledge. So what is an undecidable proposition? How long is a piece of string as an undecidable proposition? Let's have a look. Here's Strelen. This is a reasonable definition. I think this is fairly close to the one that's actually in K&R. I think I just changed one piece of notation, one or two names to protect the innocent. This will, in C, it will start at the beginning of a sequence of bytes, and it will look for the null, and it will count. Okay, it's a simple counting problem, and it will return this. Okay, under what circumstances does this work? What is the precondition? Okay, so precondition, the idea of using preconditions and postconditions to define our code, it's a very useful formal technique, but it's not actually practical in programming. So C++ 23 users will be in for a bit of a shock because it turns out it's a bit of a chocolate teapot, which is a highly inflammatory comment, and I'm prepared to do a talk on that in another year. But the point here is, what is it that we can say must be true for this to work? Can I define this? What can I say within the system of Strelen, in the system of standard C? It can't be a null pointer. Cool. Is that it? No, actually, there's a bit more. And the problem is that I can't state these in standard C in the system of Strelen. It's not provable. I cannot, looking at this code, tell you whether or not it will run correctly, because what I need is that there should exist for some n a null. There must be a null somewhere. Okay, we call this the halting problem, or this is related to the halting problem. Somewhere at the end of this, there is a null. And by the way, every position from here to the end is a valid pointer. You can't prove this. There is no way in standard C you can do this. It is not a provable thing within that system. But that doesn't mean I can't say whether or not Strelen is going to be used correctly. Of course I can. I just need to change the context. That's what we do. We change the context. We provide a context against which, and here is one that is well defined. Here is basically the code of conduct in Bill and Ted speak. Be excellent to each other. And here this works absolutely fine. What I'm going to do here, however, is this doesn't work, okay? Here we have a char sequence, and it's got 5 characters, which are all filled up, and there's no null at the end there. So what happens? Maybe there is a null somewhere, but we don't know that there are valid pointers. In other words, this is undecidable. People say undefined behavior. Yeah, you're quite right. But at this point, what we're doing is saying, actually, there will be some kind of behavior, but the point here from the system of Strelen, that was undecidable. I can visually inspect this, and more importantly, a tool can visually inspect it and go, hey, guess what? There's problems here. But we can't decide this at the level of Strelen. We can only decide this by understanding the context. Also, I can just give you garbage values. Again, that this is decidable at this level. So the point here is this is not just an artifact. People often think of the incompleteness theorem as being, oh, that's just something that exists for mathematicians. It's like actually has real consequences for how we understand and reason about our code and what is demonstrable at certain levels. And as Adrian Koller also observes, one premise of many models of fairness in machine learning is that you can measure or prove the fairness of machine learning from within itself. And people often say, oh yeah, we've used this. It's like, no, no, no. From the properties of the model itself and perhaps the data it is trained on, no. And you can't just have other data that you didn't use in that training set. You need information from outside that system. You need application context that you don't have at the time of creation. And then it becomes decidable. Fairness is a very tricky thing, but that doesn't mean we should back away from it. But you cannot do that from within the context in which it was created. So early part of the 20th century was very exciting for all these things. So a lot of things changed, and it gave rise to a lot of stuff. People were trying to figure out, what can we say about various systems? 1936, Alonzo Church addressed the Entscheidungsproblem in parallel with Alan Turing, and they both came up with the same answer, but using different things. Turing basically invented the concept of the Turing machine, which is, a superstring, effectively. And Alonzo Church basically invented lambda calculus for this. Actually invented it in 1932, but the paper in 1936 was more significant. And the Entscheidungsproblem is really a kind of a way of stating that if I give an algorithm, a program, a statement, and say, is this universally valid, that I should be able to get a yes or a no for everything. And this is very similar to a thing known as the halting problem, where can we guarantee that we can get a yes-no answer for every program that we feed something that it will always terminate. Turns out that this is undecidable as well. And we can actually give some very interesting examples where this kind of pops up and why it is that people never regard it from this point of view. So a little piece of Go here. I'm going to make a channel of strings. This is my push channel. I'm going to make a pop channel. And then I'm going to launch a stack function. I'm going to treat the stack function as an object. In one sense, I've got 2 channels, one for pushing, one for popping. Classic stack. I'm going to push Accu. I'm going to push 2021. Then I'm going to pop, and then I'm going to pop again. And so, yeah, we get what we wanted. Let's try a different scenario. I'm going to create it, and then I'm going to pop. Now it's empty. What happens when I pop from the empty one? Well, let's create a state model for what I've got here. When we create it, it is empty. We can push. It becomes non-empty. We can keep pushing and popping. Now, while the number of pushes is greater than the number of pops, it remains non-empty. When the number of pushes then becomes equal to the number of pops, or the number of pops becomes equal to the number of pushes, it becomes empty again. What happens if there are more pops than pushes? Well, guess what? It's not defined. Okay, some people misunderstand the Heartbleed state chart notation and assume that it self-transitions. It doesn't. It's actually undefined in the model. What does that mean here? Well, from a practical point of view, what I'm basically saying is, so channels, for those of you who only come across channels in Go, they're a much older idea. They date back to the late 70s, Tony Hawk. CSP, this is called a deadlock. And it turns out that we've got a very simple implementation of this function. I'm receiving two channels, my push and my pop. I'm just going to have a simple array. I'm just going to loop forever. And we simply have the idea that we append whenever we receive a push, if we're empty, and if we are non-empty, then we are receiving pushes and we are answering pops. But if we are just empty, we do not receive pops. We can also change this with this observation. We've done an iteration. Actually, we can use the call stack as our own stack. A much more elegant solution, probably more native to Erlang programmers than it is to Go programmers. And I can have my stack call a non-empty stack. And so therefore the value, my top string, is always held as the current value. We always know our top. So how do we test the correctness of this code? How do I test the fact that what I'm expecting is that if I pop an empty stack, I will never get a response? Okay, and it turns out that Dijkstra's observation here is quite relevant. But we can't show all the bugs. But the point is we can't show the absence. And actually, he didn't have the halting problem in mind. But let's have a look. Let's try and test the fact that when we pop from an empty stack, that it should never return. So we can definitely say if it returns, that's a test failure. But how do I test that it should never return? How do I can state that in English. This is the interesting thing. There's a lot of things about preconditions that I can state in English, but it turns out most of those take in a context. It allows me to touch eternity. By the way, this is not, don't go find this in the Go libraries. There is no dot eternity there. How do we actually solve this? We solve it pragmatically, I believe is the correct way of putting it. I'll time out after a second, because honestly, you know, let's call it works after a second. Yeah, I could make that a few more seconds. The key idea here, the thing I think is interesting, is that this is actually an application of the CAP theorem. I'm getting an answer based on the information that I have available. But what I've done is I've effectively kind of solved the halting problem. You know, that's kind of easy. You know, this is how you solve it. This is how we solve it. We put timeouts on things. You know, there's a timeout. We put timeouts on operations, and we don't wait for eternity. What we do is we provide boundaries. Boundaries are incredibly useful. We create a context. If I can't answer it in the context of the world, tell you what, I'm going to make a judgment call. I'm going to make things workable from my point of view. So let's kind of head out with some other considerations. This is the key observation. We're not even sure if Niels Bohr said this. Prediction is very difficult, especially about the future. What I like about this quote, and the fact that we're not even sure if Niels Bohr was responsible for it, is the fact that was in the past. I mean, we can't even get the past right. How on earth are we supposed to be able to predict the future? This has consequences. This is the unknown, unknowable unknowns. There are things that we cannot know until they arrive. And I'm not just talking pandemics here. I'm not just talking about the questions of kind of dark computer science. It comes to the very nature of our business. One of the mantras of business is we prioritize by business value. You know, I see this in a lot of Scrum guides and things like that. We prioritize our requirements by business value. There's only one problem. You can't do this. It is against the laws of physics as we understand them. You cannot time travel. Well, some of us can. Time travel is not an option because you don't know what the business value of something is until you have defined, one, what you mean by business value. It's a very vague term. It's a bit fluffy. For whom, over what time frame, and when you're going to evaluate it. The business value of something is not known until it is known. In other words, there is no way you can know the business value in advance. What you can do is prioritize by estimated business value. But that word estimate is really important. Leaving it out, it's just like some people say, oh, yeah, but, you know, we've always done it this way. This is how we always speak. No, you're speaking sloppily. If we can't tell the difference between actual numbers and estimated numbers, we are in for a hell of a long ride. And it's going to be a very bumpy one. So the great Grace Hopper observed, humans are allergic to change. They love to say, we've always done it this way. I try to fight that. That's why I have a clock on my wall that runs counterclockwise. And you know what? That's why I have a clock on my wall. Grace Hopper is the reason I did that. I remember reading this quote a few years ago, and I thought, I live in the age of internet shopping. Surely somebody out there has created a clock that runs backwards. And lo and behold, many people have. It's great. It really messes with my kids, though. I mean, they can barely read analog clocks at the best of times, but they come in my office and go, oh, I can't look at that. You know, that just messes with my head. So we have this challenge that when we look at the world and we see it, some of the boundaries are there because they help us to reason, but others are related to our assumptions. They are limited. There's a boundary on what we have chosen to know. In other words, our assumptions, if you like. And those assumptions hold us back. And we can see, I mean, there's a nice definition of assumptions that I tend to think. I tend to think of assumptions as being like Lego bricks in the dark, and you're walking in there with bare feet. Even if people tell you, guess what, you have assumptions. Please list all of your assumptions. That's not a thing that you can do, because epistemologically, these are not things that you can know until you have stepped on them, okay? You know that they're there. Well, if you're aware, you will be aware there's things that I don't know that I don't know, and you will not discover them until that moment when you discover them. An assumption is a very curious piece of knowledge. Some assumptions I can state because I have context that allows me to say, here is an assumption. It's a given. I want you to know. I'm assuming, you know, all pointers are well formed or whatever. But many of our assumptions are discovered in retrospect. In other words, you discover your assumption when somebody says, oh, this is the case. And you go, oh, I had assumed that. It was not the case. And at that moment, you've discovered you had an assumption. Before that, you didn't know you had it. So it's discovered in retrospect. And this is kind of important. We see this all the way through. And I like the way that Parnas, 50 years ago, when he talked about dependency structure in code, he wasn't talking about the dependencies the way that we tend to think of them. He said it much more broadly. In terms of the connections, he talked about the assumptions. In other words, it's not just that this module imports this module, that this class inherits from this class, that this function calls this function. Those are visible dependencies. When you ask most developers, what are the dependencies of your system? That's what they will tell you. He's actually saying assumptions. And that is a much bigger, much bigger world. When you ask most people, you're working on that piece of code. Here's other code that you and your colleagues own. When most people ask, what are your assumptions? That's what they're looking at in their system. What about the code that you don't? And we tend to kind of put that out to the side. Oh, well, that's okay. That's code that we don't own. We're reusing a library. That's somebody else's code. That's open source. That's the standard library. That's whatever. I don't need to worry about that. Of course you do. It's part of your system. It defines your architecture. You have chosen not to know about it, and a lot of the time that's fine. But here's the point. We have these transitive dependencies. What about the dependencies that those depend on? And then there are the other dependencies. Whenever I ask people, what do you depend on? Very rarely, if somebody's working on on a system, a Python code base, very rarely do they ever say, we depend on Python. But they do depend on Python, because if that changes, then that's not going to work out well. And Python has changed, Python 2 to 3. If people had said, and I actually had this with the team about 2.5 years ago, they said, I said, what about your programming languages and your libraries and your platforms and all the rest of it? Oh, well, that's not dependency. It totally is dependencies. If somebody removes that rug, you're in for a big surprise. It defines your security. It defines the viability of your product and everything. It's a massive dependency. The fact that you as a programmer have chosen to shut it out, I understand that, but it's a dependency set. You depend on it. If it changes, you have a problem. But this was a transition when Python 2 was, the clock was ticking on its life. It was going to end. You're depending on Python 2. You do know support's going to end for that. Why are you depending on Python 2? Because of another library that uses Python 2. So you can't use Python 3 because of a piece of code that is being used that you don't control. Oh, you don't control your architecture is what I'm hearing. That is the problem. People are not very aware of that context. They have a kind of like a kind of hyperbolic projection view, a foreshortened view. We also depend on things like governance, customers. Sometimes people say, without customers, life would be a lot easier. There is a certain truth to that. But these are all the contexts. If those change, if the rules of accounting change, if the rules of governance, if the market changes, suddenly the code of yours that depends on all of those, that's changed as well. And this bites us, the dependencies of our dependencies, all the way through to the invisible assumptions. A licensing model changed in 2016, which upset a particular open source provider who then chose to withdraw their libraries, which then brought down a number of sites who didn't even know they depended on this tiny piece of code for padding a string. I mean, honestly, that's not one of the hardest, the halting problem, that's a hard problem. Padding a string, that's not a hard problem. So the point here is this is in our blind spot. This is the bit that we have to watch out for. That I'll kind of close with John Muir's observation that when we try to pick anything out by itself, we find it hitched to everything else in the universe. Why? Because it depends. It depends on everything. The challenge that we have is to distinguish between the things that we are able to know and are on a journey to know. In other words, that is why we talk about practices and development process, the increase of knowledge that we are able to achieve. We always operate with incomplete knowledge. Every day when we get up as human beings, we operate with incomplete knowledge. Operating with incomplete knowledge is actually a very normal state. We're actually not bad at it. We're quite good at it. The problem that we have is when we kid ourselves that we have complete knowledge about something, that the boundary of convenience is a definitional boundary of necessity, and that's the way the world is. No, that's not true. But we must also distinguish and make the effort to try and find out this is a process of inquiry. There are questions we can ask that will help us find those boundaries and will answer questions that we have within a boundary by seeking a larger context. And that is the nature of knowledge. So thank you very much. I think I have a couple of minutes for questions. Thank you very much, Guy. Applause. There's some lovely observations that have been going by. I have not been able to keep up with them, but thank you very much. Phil Nash made a lovely observation there about left pad as a teaching example in his TDD training. Yeah, I have a worked example on this one as well. I think it's wonderfully instructive because it's such a self-contained example that had this ripple effect. We can understand it and its consequences. It lives in our blind spot. It's instructive from a testing point of view. By the way, the original left pad was actually incorrect. It had bugs. So, be careful of what you pick up on the internet. You don't know where it's been. It actually had bugs. It just happened that people happened to be dodging those bugs. But it's also absolutely fascinating because from another point of view, it was also opportunity for security breach. We're just very lucky that that didn't happen. So a couple of other questions. I've answered the one on thread unsafety. Yes, you can be thread unsafe in the context of a single thread, or to be precise, you are thread safe with respect to zero threads. Andrew Marlowe, I mentioned something about precondition checking being broken in C++23. Can you elaborate? I'm not going to say it's broken. It's just so limited. It's chocolate teapot territory. It's just so not useful. And I've only been studying the whole precondition model for, I don't know, just over 3 decades. So perhaps I know nothing on this one. Yes, I am going to drop that one in there. But that's the problem, is a lot of people come to it. They have the same fascination that I did in my 20s. It's just like, oh, that's a really cool idea. And then I put it into practice and I found the limitations. I think it's a powerful model of reasoning. As for, is it any use? Honestly, no, but people are just chucking stuff in the C++ standard at the moment just for kicks. So I'm being a little disparaging there. There's a lot of hard work that's gone in there, it's all done in good faith. I will have to come back to that one in a separate talk to explore why is it not actually very useful in its current form and what would make it more useful. It's just so incomplete that you really can't say anything of use. So I'm going to leave that one there. What are the key takeaways from this talk, Maxim asks? Honestly, I don't know. I have no idea. I think that's for discussion. My key takeaway is that in putting it together, it really clarified a number of things about the crossover between different kinds of knowledge and different models. It turns out that certain things in maths or physics actually turn out to have direct applicability, either when I come to estimation or when I'm actually dealing with things that I never really thought about. Why do we have timeouts? It's because of undecidability. That is actually that. In other words, we shut the problem off before it becomes a problem. And you know what? That's actually quite reasonable. It also, curiously enough, relates to the CAP theorem and so on, which I hadn't realized until relatively recently. And so therefore, there are these limits and these boundaries that teach us. They show us different ways of understanding our knowledge. But again, if you want one key takeaway, humility and knowledge, you will learn more by approaching knowledge that way. Another observation, thread model of your application depends on the thread model of all the libraries it uses and those libraries and so on and so on. That kind of, yes, that comment was made earlier on, but importantly, it goes back to the final dependencies graph that I showed, in the sense that the threading model, not just any threading model, any model, don't think, oh, I'm not doing threads so that I don't have to worry about it. Honestly, I mean execution model, how we choose to order time in our code, what we mean by time in our code. You are defining the laws of physics for your code. It is non-trivial, and anybody who thinks it's just adding a library and is not architectural has not really fully understand how shocking all of this is. The nature of time is quite a deep concept. So if I am using a library and it has a very strong opinion about how time flows, then I need to understand that, and I need to respond either by adopting the same model or by containing that model. And that's in other words, the mismatch between universes. It's not just, oh, there's a bug. It's a mismatch of worldviews, and that leads to bugs. We manifest it as bugs. What we fail to understand is it's two different ways of framing knowledge that have been expressed in code, and they are in collision. You know, it's two different theologies clashing. That is the pain that we are experiencing. Any other thoughts? Let's see, Lucian said, to be honest, I can't watch any of Kevlin's talk without him messing with my brain. That's one of the key takeaways. Thank you for that observation. I leave you the rest of the day to unwind these and unmess your brain. I hope that's been fun and enjoyable, and I really need to leave you to grab a coffee before the next talk. So thank you very much.